All right, so here goes. 11.7 volume and moles. So it's going to be Avogadro's law. Remember, Avogadro's number is 6.022 times 10 to the 23rd. That equals 1 mole of something. So if I had 6.022 times 10 to the 23rd of me, that would equal 1 mole of me. Yeah, I know, a big mole, just saying. All right, so learning goal. Use Avogadro's law to determine the amount or volume of a gas when the pressure and temperature are constant. All right, so let's see how this all works. All right, Avogadro's law was formulated by, butcher this, Amedeo Avogadro in 1811. States that the volume of a gas is directly related to the number of moles of gas when temperature and pressure are held constant. And that kind of makes sense because we know that volume is directly related to the amount of something in it. So V1, volume 1 over N1, okay, so a certain amount of moles is going to equal a certain amount of volume, is equal to V2 over N2. Volume is going to directly change in relationship to the amount of moles of a gas inside of that vessel, okay? All right, so the volume of gas is directly related to the number of moles of the gas. If the number of moles is double, then the volume is going to double. It's a correlation, 1 to 1, okay? So if it triples, guess what's going to happen? The volume is going to triple. So in this example here, all right, if we said that we have 1 to 1, so this is the size of 1 mole to 1 liter, and then we got here 2 moles, 2 liters. If I had 14 moles, what do we think we'd get? 14 liters, right? Direct correlation. So if 0.75 mole sample of helium gas occupies 1.5 liters, what would the volume of 1.2 mole sample of gas occupy at the same temperature and pressure? Remember, this being constant, okay? Well, how can we figure that out? What are we going to look for? We're going to look for volume. So first thing we do is, you should know by now, organize our data, all right? Make sure it's in the correct spots. So V1 is 1.5 liters, N1 moles is 0.75 moles, N2, we got 1.2 moles, and we're going to look for volume 2. Now we got to take our root formula and turn it into searching for V2, all right? Very easy to do. V2 is already on top. We're just going to bring N2 right up there, okay? And it becomes V2 equals volume 1 times the moles 2 over the moles 1 from the first part. Then what do I say? We've got it all set up. What are we going to do? Plug and chug. We plug in the numbers. All right? So we're going to substitute the values in. Our V1 is 1.5 liters. Our new moles are 1.2 moles. And our old moles, N1, is 0.75. See how the moles will cancel, okay, because we're searching for liters, so that's what we're going to be left with. So we go 1.5 times 1.2 divided by 0.75. That gives us 2.4 liters of volume, okay? Now, if I said the new moles were 1.5 moles, well, that is going to double, all right, that 0.75. So our new liter value would actually be 3, right? Because 1.5 times 2 is 3. Very good, all right? So the volumes of gases cannot be compared at STP. STP stands for not stone temple pilots, but standard temperature and pressure. When they have the same number of moles of gas, standard temperature is exactly 0 degrees Celsius or 273 degrees Kelvin, or exactly 1 atmosphere or 760 millimeters of mercury or 760 torr. Okay, I really do like the word torr just because it's easier to say. All right. So at STP, 1 mole of any gas occupies a volume of 22.4 liters, approximately equal to the volume of about 3 basketballs. All right. So understand that 1 mole of any gas occupies a volume of 22.4 liters at STP. All right. So it could be oxygen, it could be hydrogen, it could be nitrogen, it could be the carbon dioxide. Regardless of what it is, 1 mole of carbon dioxide will be 22.4 liters. 1 mole of oxygen will be 22.4 liters. Doesn't matter. Okay. And that equals the volume of about 3 basketballs, approximately. So when a gas is at STP conditions, remember, 0 degrees C, 1 atmosphere, its molar volume can be written as a conversion factor and used to convert between moles of gas and its volume in liters. 1 mole of gas equals 22.4 liters. Constants. These are constants. Remember, we've got constants. All right. So, and it shows the relationship here. 1 mole over 22.4 liters is equal to 22.4 liters over 1 mole. Perfect. So if I were to right now just throw out 2 moles of gas, what volume would it occupy? Well, 2 moles of gas, 1 mole equals 22.4, and I'm doubling the amount of moles. Guess what the volume's going to do? It's going to double as well. So that's going to give us 44.8 liters of volume. Direct relationships. So, guide to using molar volume. State the given and the quantities, needed quantities. Okay, organize. Write a plan to calculate the needed quantities. Write the equalities and the conversion factors, including 22.4 liters at STP, 0 degrees Celsius, 1 atmosphere. Okay, and then set up the problem, and then cancel units. Everything that we've been doing thus far. Okay, so what is the volume occupied by 2.75 moles of nitrogen N2 gas at STP? Well, what's given? 2.7 moles of nitrogen. Okay, at STP. What's needed? Liters. Okay, well, what do we already know? 1 mole equals how many liters? I'm waiting for an answer. I don't hear you guys. 22.4. Very good job, Bob. Great answer. Yes, 22.4 liters. Okay, that is 1 mole. All right, there we go. See, 1 mole and 22.4 liters. Great. So we set it up. All right, well, we got to get these moles to cancel, and we know 22.4 liters over 1 mole. Boom. The moles will cancel, right? So we simply are going to go 2.75 times 22.4, giving us 61.6 liters of nitrogen, right? Straightforward. Not too bad. Once you set up your formula, plug and chug. All right, at STP, the density of a gas is calculated by using molar mass of the gas and molar volume. Remember, density, whether it be a solid, liquid, or gas, is mass over volume. Okay, we're just talking about molar mass and molar volume, which is just an expression. So balloons rise in the air because helium is less dense than air. You know, another experiment you could do is in a car. If you get a helium balloon, put it in the back seat and then floor it, okay? And most people think that the balloon will go back towards the rear of the car. But what actually happens is the balloon goes forward because the balloon is filled with helium, which is less dense than air. And the air, because of inertia, will push that balloon forward. Anybody that's ever driven with helium balloons can remember swatting the balloon back, you know, because it's hitting their head. So this is kind of a combination of chemistry and physics. This is why science is so beautiful. It's all interrelated. All right. So it says calculate the density in grams per liter of oxygen gas at STP. state given and needed quantities. So we need to know the amount of O2 gas at STP, and we need to know the density of oxygen at STP. So we got to write a plan. Okay, well, we know density is mass over volume. All right, cool. The moles will cancel, so that's going to give us grams per liter. All right, so 1 mole of oxygen is 32 grams. Well, how do we know that 1 mole of oxygen is 32 grams? Well, it's easy. We know that the atomic mass of oxygen is 16. And how many oxygens do we have there? It's O2. Well, we go 16 times 2. That gives us like 32 grams, all right? And we know that 1 mole of oxygen is 22.4 liters. How do we know that? It's a standard at STP. So, since we know this, we can go ahead and set up the problem with our factors so we can get it to cancel out, okay? So, if we look at this, mass over volume, all right, we've got 32 grams, all right, that's our, oh, my thing froze here, we do that, oh well. We know, I don't know what I'm doing. Let's take it from the top, shall we? There we go, I got to unfreeze. All right, is this where we're at? We're one step further. We're one step further. Okay, so we got 32 grams up top. Right there, 32 grams, and that's per mole. And we got 22.4 liters per mole. So we can go ahead and just whip those out. Just be, cancel. And that's going to leave us with grams, and that's going to leave us with liters. Okay, then we simply go 32 divided by 22.4, our constant. Awesome, because right there. And since we know mass over volume, the density of oxygen, okay, is going to be 1.4 grams per liter. That is the density of oxygen. All right. And that's it for that. All right. So we're going to get a little more complicated next round, and we'll go from there.